nature of the universe and what is it made of? What are matter, energy, space, and time? How did we come to be here and where are we heading?
The effort to answer fundamental questions about the universe has reached a critical turning point. At the beginning of the 21st century, physicists had a clear understanding of the properties of particles and forces that make up the ordinary matter around us. But astrophysical and cosmological observations from space stations show that this picture of the universe is incomplete.
Because 95% of the universe's composition is not ordinary matter but something else mysterious. That is dark matter and dark energy. Thus, we realize that we actually know nothing about most of what constitutes the universe.
To understand this unknown part of the universe, we need new discoveries in particle physics. Astronomical observations help us study cosmological parameters.
Accelerators help us build a quantum solution for those parameters. The energy achieved in today's accelerators has approached the conditions of the first moments after the Big Bang, serving as tools to help us explore dark matter and dark energy.
This is the time for a revolution in the understanding of fundamental particle physics in the universe.
Never before have the approaches from cosmological observations and accelerator experiments supported each other so closely. Experiments being and to be conducted in fundamental particle physics at laboratories worldwide will give us the ability to answer questions about the fundamental physical laws governing the universe. These questions are both familiar and profoundly revolutionary, guiding fundamental particle physics in the 21st century.
From the beginning, theoretical physicist Einstein dreamed of unifying the forces.
This dream can be said to have been quite well realized within the quantum microcosm, or the Standard Model. However, those quantum ideas do not apply to the cosmic scale. There may still be some missing elements. Gravitational fields,
Dark matter, and dark energy must have a quantum explanation.
There must be a theory that encompasses
Both the Standard Model and general relativity,
while also solving the mystery of dark energy. Our research so far on the fundamental laws of nature has helped us realize that physical laws and the existence of material particles are governed by underlying natural symmetries. Some of these symmetries disappeared right from the Big Bang. One of those lost symmetries might be supersymmetry.
Supersymmetry predicts that for every ordinary particle, there is always a supersymmetric partner particle.
Supersymmetry theory, the core of string theory, suggests that one of these partner particles, the neutralino, is a candidate for dark matter and may be related to dark energy.
The discovery of supersymmetry is clearly an experimental challenge for fundamental particle physics. Not to mention the detailed study of the structure and properties of supersymmetric partner particles.
Recent measurements with telescopes and space stations show a mysterious force, dark energy, filling the vacuum, driving the accelerated expansion of the universe.
We do not know what dark energy is and what it exists for. On the other hand, fundamental particle theory tells us that at the microscopic level, even a perfect vacuum is filled with quantum particle pairs, which should be a natural source contributing to dark energy. However, preliminary calculations of the dark energy generated from that vacuum give a value 10 to the power of 120 times larger than the observed value.
Thus, there must be some unknown physical process that cancels out most of that vacuum energy, leaving just enough to drive the expansion of the universe as we see it. A new theory in fundamental particle physics is needed to explain this process. Experimental data lead to another hidden component of heavy space, which is the Higgs field. This field provides mass to particles. Without the Higgs field, electrons would move at the speed of light, and atoms would decay immediately. Are dark energy and the Higgs field related? The discovery of supersymmetry might reveal that connection.
It could explain the small but influential value of dark energy.
The revolutionary idea of string theory is to realize Einstein's dream, but the most fundamental explanation for everything, from the smallest particles to the entire universe.
String theory unifies all physics by describing every force and particle
as different vibrations of a single entity called the superstring.
Does the superstring exist? The strings themselves may be too small to observe directly.
But string theory makes some testable predictions.
This theory requires supersymmetry and predicts the existence of 7 undiscovered spatial dimensions. These extra dimensions are the main reason for the complexity of the particle physics mission. Verifying the correctness of string theory is finding those extra spatial dimensions. How many extra dimensions are there?
What are their shape and size? Why are they hidden?
Are there any new particles related to those extra dimensions? At the most fundamental level, particles and forces may converge through hidden principles like grand unification, or through new physics like superstrings. Physicists have found many types of fundamental particles and determined quite detailed properties of each.
What is their role? How do we know when we have found all types of particles?
We have discovered 3 families of quarks and leptons, the most fundamental component. These 3 families differ only in mass,
from less than a millionth of the electron mass to the mass of a gold atom.
Similar to how quantum mechanics helps explain the periodic table of chemical elements. Today, we are searching for new theories to explain the properties of fundamental particles.
Why are there 3 families of particles and why do their masses differ so much? Why are the properties of quarks and leptons completely different?
Most of the matter in the universe is dark.
Without dark matter, stars and galaxies could not have formed.
And life today would not exist.
Dark matter binds the universe. What is it?
In fact, the existence of dark matter was proposed as early as the 1930s. But only in the last 15 years
have scientists made significant progress in understanding its properties, mostly determining what it is not. Recent observations of dark matter's effects on cosmic structure show it is unlike any known or laboratory measured form of matter.
While many theories have emerged to explain what dark matter is. For example, supersymmetry theory predicts new families of particles interacting very weakly with ordinary matter, and the lightest among them to be the dark matter particle. Neutrinos are the most mysterious of the known particles in the universe. They always bring surprises, interacting with other particles so weakly that millions of neutrinos pass through our bodies every second without leaving a trace. The Sun also emits countless neutrinos generated from fusion reactions in its core. These neutrinos are born as only one type, but on their way to Earth, they mysteriously transform into 2 other types. Neutrinos have mass, but the heaviest neutrino is only a millionth of the mass of the lightest charged particle.
The fact that neutrinos have such small mass
may be because they acquire mass from an unknown physical law, possibly related to the unified force. Studying the detailed properties of neutrinos' mass,
how they transform from one type to another and whether they are their own antiparticles, will tell us whether neutrinos are ordinary matter particles or something else.
What initiated the Big Bang?
How space, time, matter, and energy acquired the forms we see today.
Whether we can reverse the history of the universe. The processes in the early stages occurred at extremely high temperatures and matter densities, which determine the fundamental properties of particle physics. Those processes were finely tuned to allow the formation of galaxies, stars, and planets. Whether there exist physical laws we don't yet know
that determine human existence.
According to current theory, the universe began with a strange explosion, followed by an extremely rapid expansion of Earth. To understand the phenomenon of inflation, breakthroughs are needed in our understanding of fundamental physics, about quantum gravity and unified interaction theories. Although the conditions of inflationary expansion correspond to energies to recreate on Earth, we can still observe its traces through the remaining cosmic microwave background radiation. After the period of inflationary, extremely special physical condition allowed the culmination of fundamental particles into a new phase of matter. As the universe expanded and cooled, that was precisely the phase transition, like steam condensing into water.
And these phenomena leave observable traces today.
The cosmic phase transition phenomenon can be recreated in experiments at high energy accelerators. The Big Bang almost certainly created particles and antiparticles in equal numbers. However, all observations in the observable universe
show that we live in a universe of matter, not antimatter. What happened to the antimatter? Perhaps from the beginning there was a small imbalance between matter and antimatter. Or antimatter was completely annihilated into photons and neutrinos. Today, physicists observe in laboratories a very small asymmetry between matter and antimatter. However, understanding these asymmetries is still incomplete, insufficient to explain the dominance of matter in the universe. Is there perhaps a still mysterious phenomenon causing a different evolution between matter and antimatter? The origin of this phenomenon relates to the Higgs boson, or to symmetry, or to remnants of space.